ready, we will start in just a second. So let me change this, pull up the chat. All right, and I am recording today. I had a few requests, so this recording will be posted later today. All right, so we're continuing with chapter 3, and hopefully you're keeping up with the readings. Still, I know that it's starting to get exam time, but please make sure that you're reading chapter 3. It's really helpful. The book lays it out pretty well, and this chapter can be confusing for some. So first, a brief reminder, which you should all know from your previous classes and the prerequisites. An EOS is what we call an equation of state. Equation of state. And this is any equation that relates pressure, volume, and temperature of a substance. So any equation that relates pressure, volume, temperature of a substance. So the main equation of state that we use, and you've probably seen before, is PV equals nRT. This is the ideal gas law. And we're going to be using a modification of PV equals nRT in this class where we use P specific volume equals RT. So essentially we're including this moles term as a mass term, dividing it by this volume, getting specific volume. So this equation of state is what allows us to look at ways of calculating pressure, volume, and temperature, also specific volume of different situations, like we were doing with the steam tables on Wednesday. And the way that we do this is through a concept called compressibility. Compressibility. And we've talked about incompressible fluids, fluids that don't have any compressibility. Typically, these are like liquids. But with a lot of gases or even liquids that have some vapor in them, there is a certain level of compressibility that's occurring there. So we use this compressibility with the letter Z, and Z represents the compressibility factor. Compressibility factor is Z. So remember from Monday, X is quality, so how much of the mass total is vapor. We also use this term throughout the chapter Z, which is a compressibility factor. This compressibility factor, what we consider it to be is the deviation from ideal. So we have this ideal gas law, but then we also have this Z term, which allows us to determine how we are deviating from an ideal situation. So deviation from ideal gas. It's also called a correction factor. So typically, we're not, in this chapter, we're not looking at ideal gases, we're looking at real gases. So gases that are behaving in a real way, not an idealized way. So we use for real gas. So it's a correction factor that corrects this real gas term for an ideal gas. And importantly, Z, our correction factor here, is going to be related to our ideal gas law. And we are also going to be using this equation where our specific volume actual over our specific volume ideal. And as you can see here, Z is equal to 1 for an ideal gas. So your correction factor doesn't really happen, right? You don't have to correct for an ideal gas. You have no deviation from ideal. Your actual specific volume is your ideal specific volume. All right. Okay, so we use compressibility with this letter Z to correct for real gases in comparison to ideal gases. And then, so on page 136 in the 9th edition and 8th edition, and page 137 in the 3rd edition. So it's all about the same place. You have more information about these equations of state and where this compressibility comes from. We can also look at including this correction factor in our ideal gas law up here. So if we include compressibility in here, we would have P, our specific volume, is equal to ZRT. So we can include the compressibility factor in the ideal gas equation, as well as using this V actual over V ideal for specific volume. All right. So this starts on page 136. And the next concept that is introduced is the concept of reduced pressure and reduced temperature. So first, we're going to look at reduced pressure, P sub R, and reduced temperature, which is T sub R. And this is on page 141 in the 3rd edition. I think it's pretty close in the later editions as well. I keep books at home and in the office and everywhere, so I'm trying to get as close as I can. Okay, so gases behave differently at different temperatures and pressure, and a lot of times we're interested in normalizing the pressure that we have to the critical pressure that's available, which gives us this reduced pressure or reduced temperature. So for our reduced pressure, P sub R, this is going to be governed by our pressure over our pressure critical. And it's the same for our temperature. Temperature reduced is going to be our temperature over our temperature critical. All right, so our pressure is just our pressure of the system, and then our critical pressure is a value associated with whatever gas or substance we're looking at. Our temperature is the temperature of our system, and then our critical temperature is a value associated with whatever substance that we're looking at. So if we are interested in finding our critical pressure or our critical temperature, we're going to use table A1. So for critical pressure and critical temperature, here's where we're going to use table A1. In my book here, it's on page 988. Yours should be close. If it's not, go to the first page of your appendix 1 and it gives you an index of where these are, and you're going to try to find the table that has molar mass, gas constant, and critical point properties. So this temperature critical and pressure critical are associated with their critical point, which is one of the definitions that you need to learn on your own, read on your own from the chapter. So we can use table A1 to look up our critical pressure and our critical temperature. So as an example, please find this table, and I want you to type into the chat what is the critical temperature for water and the critical pressure for water. Okay, well, Abed, just find table A1. Yes, so Brianna, Ida, Justin, 641 Kelvin is our critical temperature, and 22.06 megapascal is our critical pressure. Okay, so 882 in the 9th edition. So I'm using the book that I used when I took thermo in my undergrad. So it is like 13 years old now. So they've obviously changed some pages around. Okay, great. So at least some of you have been able to find table A1. You've been able to find on the right-hand side of the table where we have these critical point properties. So we have critical point for temperature, pressure, and volume that is occurring over there. And we can look them up in that table. All right, continuing. So I'm going to clear this. All right, a lot of times we're interested in this pressure reduced and temperature reduced because we are going to use them in something that's called a generalized compressibility chart, which we also shorten to GCC. Generalized compressibility chart. So the generalized compressibility charts, in the 3rd edition, it's on page 1030. Page 1030 in the 3rd edition. In the 8th edition, I believe it's on page 922. Page 922. And this chart is labeled as Nelson Obert generalized compressibility chart. So can somebody type in the chat what page this is on in the 9th edition? I think it's figure A15. That's what it's labeled in the 8th edition as well, at least. So the chart should look something like this spider web. It's on page 905, 906, great. Okay, so thank you everyone. In the 9th edition. So the generalized compressibility chart, or the GCC, allows us to use reduced temperature and reduced pressure to solve for things like specific volume, temperature, pressure, or any of these things that we're solving for in this chapter, typically specific volume, pressure, or temperature of a system. So the generalized compressibility chart is empirical data about the connection between reduced pressure, reduced temperature, and the pseudo-reduced volume. I don't use pseudo-reduced volume a whole lot because it's one of the more complicated terms, but these charts relate our reduced pressure, reduced temperature, and then this specific volume reduced, which is what we call, specific volume reduced is what we call pseudo reduced volume. And its equation is the specific volume over our gas constant R times our temperature critical divided by our pressure critical. So once again, similar to our reduced pressure and our reduced temperature, these are dependent upon our critical point temperatures, but then there's also this factor of the specific volume that's there. All right, so when we're looking at the generalized compressibility chart, we have two charts. There's chart A and chart B. Chart A at the beginning, at the top, says low pressures. Tell me if it says something different in your book, please, just so I can make sure that everybody doesn't get confused. So these are from temperature, reduced pressure between 0 and 1. You'll use A. And for B, this is where you're going to use intermediate pressures, higher pressures, intermediate pressures, which is between our reduced pressure between 0 and 7. The way that this chart is oriented is we have our compressibility factor on the Y. We have our reduced pressure on the X. And then we have, going this way, we have our reduced temperature. And going this way, we have our pseudo-reduced specific volume. All right, so I'm going to do an example problem where I'm using all of this because talking about it is not particularly helpful in my opinion. People learn in different ways. Yeah, this says our specific volume pseudo-reduced is what this is. All right, so I'm going to do an example problem. And I would like everybody to open this generalized compressibility chart and table A1 as well. So just turn to the back of your book, get in your appendices, and I'm going to start an example problem. All right, so for this example problem, determine the specific volume, of R134A, which is a refrigerant, at 0.5 megapascal and 100 degrees Celsius. So for part A, it says to use the ideal gas equation of state. Use ideal gas equation of state. For part B, use the generalized compressibility chart. Use GCC. And for part C, compare errors with actual value. Compare errors with actual value. All right, so for part A, we're going to use the ideal gas equation of state, which is just PV equals RT. I've hidden the mass term inside the specific volume. And using table A1, or I think it's also on the last page of your book, but in table A1, you can also find it. In table A1, you can look up the specific gas constant for each of these different gases. So the specific gas constant, or the gas constant R, which has units of kilojoules, kilogram, Kelvin, for R134A, is going to be, so I go all the way down to tetrafluoroethane, parentheses R134A. It's the fourth up from the bottom. And I can go across to the gas constant, and the gas constant here is 0.08149 kilojoules per kilogram Kelvin. All right. So can somebody confirm to me these are the same units at the top of your table? Okay, great. So then there should be a little asterisk down at the bottom of the table that says the units kilojoules per kilogram Kelvin is equivalent to kilopascal cubic meter kilogram Kelvin. At the asterisk at the bottom of the table, hopefully that also is in your book. So we can choose, thank you, Brianna. We can choose which one we want. I know for this problem we were given megapascal, so I'm going to choose the one that already includes Pascal. So I'm going to choose 0.0815 kilopascal cubic meter kilogram Kelvin. All right, and then we know that pressure is given. So we have our R value. We know pressure is 0.5 megapascal. So how many kilopascals is 0.5 megapascal?
1,000.
How many kilopascals is 0.5 megapascal?
500.
Yes, thank you, Elizabeth. Great, thank you. 500 kilopascal. And I'm going to convert to kilopascal because I know that's what I'm going to have to convert one of them one way. So it's probably just easier to convert it right now. And then I know my temperature to be 100 degrees Celsius. So this is 100 plus 273.15 would be 373.15 Kelvin. So now I have my R value, I have my P value, I have my T value. I'm asked to find my specific volume. So I have everything, I can just plug and chug. So I can isolate my specific volume is going to be equal to RT over P. And R is 0.0815 kilopascal cubic meter kilogram Kelvin. T is 373.15 Kelvin. And P is 500 kilopascal. So I have kilopascal that cancel, I have Kelvin that cancel, and I'm left with cubic meter per kilogram, which are units of specific volume, so that's good. And so plugging this in, 0.03, oh, I'm sorry, 0.0634 cubic meter per kilogram is for part A. So for part A, our answer is 0.0634 cubic meter per kilogram. This one should be pretty easy. It's related to what you've done in chemistry and physics, I imagine, so pretty straightforward. Anyone need more time writing? All right, well, this is recorded, so you can always go back. Actually, I'm gonna leave up the first part. So for the second part, we're going to use the generalized compressibility chart. This is where the real learning happens. So please make sure to ask any questions in the chat and let me know if anything is confusing. So for part B, we're going to use the generalized compressibility chart. And we want to determine the specific volume using this generalized compressibility chart. So one thing that we already know, when we have the ideal gas equation of state, the generalized compressibility or the compressibility factor Z, we can use as just a correction factor. So we can, if we can find Z, we can use it to just correct for this part A. Since A is telling us if this is an ideal gas, R134A is an ideal gas. Part B is saying it's not ideal, it's a real gas. Here's a correction value to help you see how it's really behaving and it's deviating from ideal. So for part B, we want to try to find this compressibility factor of Z. And we're going to need to use the generalized compressibility charts. So in order for us to use these charts, we need to use the values that we know to find either specific volume, pseudo-reduced specific volume, reduced pressure, or reduced temperature. We're given pressure and temperature, so it's going to be easier for us to find reduced pressure and reduced temperature. So our reduced pressure term is pressure over pressure critical, and our reduced temperature term is temperature over temperature critical. So please find the critical point pressure and temperature for refrigerant R134A. Type it in the chat. Yes, Brianna, that's right. So in table A1, we're still using that critical point properties. So our pressure, critical pressure is 374 point, I'm sorry, that's my temperature. My critical point pressure is 4.059 megapascal. And my critical temperature is 374.2 Kelvin. Was anybody not able to see where that is, where we found that? Okay. So it's in table A1, it's on the right-hand side, critical point properties. Make sure that you can find this. So we know that our pressure is 0.5 megapascal. We don't even need to do any unit conversion. We know our temperature is 100 degrees Celsius, but we need to convert it to Kelvin again. We just did this in the last part. So 373.15 Kelvin. So our reduced pressure becomes 0.123. And our reduced temperature becomes 0.99. So this is our reduced pressure. This is our reduced temperature. We want to find Z. So now we can go to our generalized compressibility chart. So please go to your generalized compressibility chart and make sure that you are following along. So I'm going to open my own generalized compressibility chart because I can't show you my book very well. It looks generally like this. So we know that our reduced pressure is 0.123. And we're going to be using the top A, generalized compressibility chart, because it's a low pressure. It's between 0 and 1. So we can go here, 0.1, and then, there's lines in your book, but 0.123, probably about here. We're going to go all the way up until we connect with the line for our reduced temperature. Temperature are the ones going this way. Specific volume are the ones going this way. So we need to find the temperature reduced that corresponds with 0.99. So here we have 3, 1.1, 1.15. Here's 1. So it's going to be about this line, maybe just a little bit less, but 0.99, I'm going to say that's really close to 1. So I need to meet up with this line at my 0.12 reduced pressure. So now I'm going to come up here. I'm going to go until I meet up with my, that's 0.9, 0.95. All right, I just met up with my temperature reduced line of 1. And now I'm going to come over and see what Z value, compressibility value I'm at. So I'm going to say that's about 9.6. I'm just a little bit over the halfway mark, 9.6. So try to do this in your own book and see that you're also getting 9.6 by meeting up your reduced pressure and your reduced temperature line. I'm sorry, 0.96. Did I say 9.6? 0.96.
I'm sorry for interrupting. What page is this on the original Sungo? I feel like I'm looking at the wrong chart.
All right, so these give us a Z value of 0.96. Did anybody not understand how I get that? Anybody not understand what I did? If you're a little off, like if you did 0.94 or if you did like 0.98, yes, that's fine. But if you are below 0.9, then you didn't do it right. If you are like above 1, well, first of all, that wouldn't happen, but that doesn't make sense. That's not close enough. If you're off by a little bit, that's fine. And on the exam, the next exam, I give you the generalized compressibility chart printed out. So you can always mark on your chart what line you're following. So it's going to be something like this on the exam. So you can always mark with your pencil where you're getting your values from, what lines you're following, where you're getting your values. So even if you're off a little bit, I can see that you were still following the correct lines. All right. So we have our generalized compressibility, or we have our compressibility factor, 0.96. And so now we have that equation where our compressibility factor is equal to our V actual over, or our specific volume actual over our specific volume ideal. We know our specific volume ideal from part A, and we know our Z value because we just found that. So then we can rearrange this. Our specific volume of our actual real gas of R134A is our compressibility factor times our ideal specific volume, or 0.96 times 0.0634 cubic meter per kilogram, which gives us 0.0608 cubic meter per kilogram is our specific volume for part B. Golly, I did it again. Anyone confused or not following along, missing something, need me to go back over something?
So for the compressibility chart, also sorry if there's like weird noises in the background, it's my chickens. For that chart, for the temperature line, we would just follow it to the left, like follow the curve, and then that's where the temperature value would be.
The table is very tiny, you can barely see it. What table? I couldn't hear you, Emma.
Okay, can you hear me now?
Yes, I can hear you.
Okay, I was just asking, like, for the general compressibility chart. Sorry for the background noise. That's my chickens. They are like right next to me. They're really annoying. For that chart, for the temperature value, we would just follow the line, like the red line to the left, like follow the curve, and then that's what the value would be, like lined up with the pressure.
I'm not sure if it's red. In my book, it's all the same color. But yeah, so you it's really easy for you to find reduced pressure because that's just on the x-axis. You just find it.
Mhm.
The tricky part is lining it up with the reduced temperature line because this is like that curving line, and all the way up near the top, it does get really congested and small. So yeah, you're just gonna line up your reduced pressure and then follow with your pencil, follow the line for reduced temperature until it meets up together, until they meet up. And then you're going to use that to figure out your Z value. You could do it in the reverse. If you were given reduced pressure and Z value, you could just connect those and then follow down that line and figure out what the reduced temperature was too.
Okay, thank you. That makes sense.
So Noah, the Z value is on the y-axis. So that's where we found the Z value from. And Abed, yeah, it's really small. I mean, if it'll be a little bit bigger on the exam, but if you need a magnifying glass or something, you can use that. And if you want to, there are a lot of generalized compressibility charts available online that are a little bit bigger and you can zoom in on your computer. So you can always look it up online for the homeworks. All right, other questions from anyone? All right. All right, so I'm going to move on. So now we know that our actual value using the generalized compressibility chart is 0.0608 cubic meter per kilogram. And then we're going to find the error. So which of these is the more right answer when we look up the correct answer? So Monday, not last week. It seems like a long week. On Monday, we were going over how to use the steam tables in the back of the book to find things like pressure and volume and temperature. So for part C, we're going to compare with the actual value. The actual value is in table A13. So first of all, is this a compressed liquid? No, the Z value, if you remember, Z is a correction factor. So Z corrects for the ideal gas. It corrects for an ideal gas to a real gas. It explains it way more on page 136. If you're still a little confused by the concept, I definitely would read it. But it's just a correction factor, or it's showing how there's a deviation from an ideal. All right, so first of all, is this a compressed liquid, a superheated vapor, a saturated liquid, a saturated vapor, or a saturated liquid vapor? It is actually a superheated vapor. We are using the ideal gas law, which means that it is in a gaseous phase. If we look at the table A13, which is the superheated refrigerant R134A. R134A superheated vapor table. Here's where we're going to be looking up our value. So we know that so another way that we know this is if we look at our saturated liquid vapor region. If we look at this table at 500 kilopascals, which is 0.5 megapascals, 500 kilopascals, our saturation temperature is 15 degrees Celsius. And we are way higher temperature than this 15 degrees. So we're going to be in the superheated vapor table, which is the next table over, which is table A13. And we're going to be looking at table A13, which is for our refrigerant, not for water. So in this table, along the way that it's kind of laid out is we have our temperature, specific volume, yada, yada, yada. And on the top, there's pressure equals whatever value in megapascal. So is everybody seeing that? 15 degrees is from the table. I just looked up this value from the table. It is on page, I'm not sure, page 918 or something, 903, sure, yeah. And along the top, we have this pressure equals a certain value. So we know that we're interested in pressure at 0.5 megapascal, which is on the next page. So pressure equals 0.5 megapascal. And then we can look up the specific volume at 0.5 megapascal at 100 degrees Celsius, which is what? So it's 0.58053 cubic meter per kilogram. All right, so based on looking it up in the table, we know that the specific volume at 100 degrees Celsius and 0.5 megapascal should be 0.058053 cubic meter per kilogram. And in part A, we found that it was 0.634, and in part B, we found 0.068 cubic meter per kilogram. So we can see right off the bat that the generalized compressibility table was closer. But if we want to actually calculate the error, so error from A, the error that we're going to do here is our, so we're going to have our ideal minus the actual over the actual. So for error, we're going to have our ideal minus actual over actual. I forget what the book says to use for the ideal. All right, I don't see anything in this edition, but so we're going to do this 0.0634 minus 0.058053 cubic meter per kilogram over 0.058053 cubic meter per kilogram. So some people say like where you're going minus where you're coming from over where you're coming from. There's a lot of different ways of like doing this error equation, but like what you think minus what you know over what you know, whatever makes the most sense to you, you don't have to stick with my terminology. All right, so this error here is 10.76%. And then the error for B is going to be our ideal over our minus our actual over our actual. So 0. No, the ideal is from our ideal gas equation of state. The 0.0608 is from our corrected real gas generalized compressibility chart. So the error for B is going to use 0.0608 minus our actual 50853 cubic meter per kilogram over 0.050 or 8053, too many numbers, cubic meter per kilogram. And this is going to be an error of, well, times 100. You should all know how to do percentages. I'm being kind of lazy about that. Is 4.7% error. So you can see that the generalized compressibility chart is much better at approximating and correcting for real gases than just using the ideal gas law equation of state. All right, any questions about anything? Okay, so A, we use the ideal gas law, so I'm calling this like our ideal equation. B, I'm calling our corrected equation. And C is our actual value that we looked up from an empirical table. You got 9.2 for this one? Did anybody else get 9.2?
No,
got-
I didn't. I got 4.7.
Yeah, I got 4.7 again too. I think maybe you missed a 0 or something, Noah. Yeah, I still got 4.7. Yeah. Oh, for A. Oh, maybe. I do these on my calculator and my phone, which isn't the best calculator to do, but the batteries died in my other one and I haven't bought new batteries. So yeah, I got 9.22. That's fine. 9.2. Close enough. It's still better to use generalized compressibility. All right. Let me correct that in my notes. All right. So I'm going to ask you all to do one yourself so you can practice this. This is example 311 in your textbook. So determine specific volume of R134A refrigerant at 1 megapascal and 50 degrees Celsius. And you're going to do the same thing. So for A, use, so for this one, it says A, use the steam tables, which are the tables in the back of the book. B, use the ideal gas equation. And C, use the generalized compressibility chart. So you don't need to do error for this one. Is the first error the corrected and the second error is the ideal? So for A, I calculated the error from the ideal, and then for B, I calculated the error from the corrected, but I compared them against the empirically, scientifically actual volume from the that I looked up in the back of the book. So I compared my calculations from part A and part B to ones that I didn't calculate. I just looked up in the book for the errors. Okay, so I want you all to work on this and type your answers in the chat once you get them.
So for the steam table, that's the superheated refrigerant one, right?
Yes, so you need to determine which steam table you're using, but you know that you need to use a superheated. But I call all of those tables in the back of the book with the saturated liquid vapor and the superheated vapor, those are all considered steam tables. What is the general name for this topic of questions? Properties of pure substances is the name of the chapter. All right, so I'm going to go over in just a couple minutes. Does anybody have the international version of the textbook? Just type in the chat yes if you do. Okay. Okay. I have another example problem that uses English units, but they don't have the right tables in the international book, so I will not do that. All right, in the interest of time, I'm going to start going over the answer. So if you're not done yet, I apologize, but I want to make sure that nobody's confused. So for part A, you just need to look up in the steam tables in the back of the book, 1 megapascal pressure, temperature of 50 degrees Celsius, and then, so it's in table A13. So we're looking for the specific volume, 1 megapascal, 50 degrees Celsius. So it's 0.021796 cubic meters per kilogram. And for part B, you're going to use the ideal gas equation. So P specific volume equals RT. And we can look up R in table A1. So R from table A1 for the superheated vapor, we already looked up before, but I believe it's still 0.08149 kilopascal cubic meter kilogram Kelvin. We know that temperature is 50 degrees plus 273, which is what, 323 degrees Kelvin, 323.15 Kelvin. And we know that pressure is equal to 1 megapascal or 1000 kilopascal. So we have everything that we need to solve. So our specific volume is equal to RT over P, which is equal to, let me remove this, 0.08149 kilopascal cubic meter kilogram Kelvin. Temperature is 323.15 Kelvin over pressure, which is 100 kilopascal. And we get 0.026 cubic meter per kilogram for part B. This is part A. This is part B.
Question.
Yes.
Can you do the unit breakdown real quick? I don't know why I'm not seeing the kilopascal per. How does it get from in the table kilograms, kilojoules per kilogram Kelvin, to kilopascals if pascals is Newton meters squared.
So if you look at the little asterisk at the bottom of the table, so at the very, like after xenon, that very last part of the table at the very bottom, there's a little asterisk that says the unit kilojoule per kilogram Kelvin is equivalent to, do you see that?
Oh, okay. Yeah, I see that now.
Yeah, so I didn't do that unit conversion myself. I just picked the one that I wanted to use. And
Got
since
it.
I'm working with Pascal, that's the one I chose.
Got it. Thank you.
All right, so part C is the hardest, I think. So we're using the generalized compressibility chart. We're given pressure and temperature, so we're going to want to find our pressure reduced and our temperature reduced to then find our Z value. Then use that Z value as a correction for part B, which is our ideal gas. So our pressure reduced is our pressure over pressure critical. Our temperature reduced is our temperature over temperature critical. So our pressure here is 1 megapascal. And our pressure critical, which is also in table 1 for R134A, is the same as last time. So 4.059 megapascal, which gives us a P reduced value of 0.246. Our temperature is going to be 323.15 Kelvin over 300, sorry, over our temperature critical, which we look up here is 374.2 Kelvin. And this gives us a temperature reduced term of 0.863. So if we come to our generalized compressibility chart in the back of the book, we know our pressure reduced. We can use A, which is our pressure between 0 and 1. We're using that top one. Then we can go to 0.2 and then about halfway, 0.2 and 0.25 about. And then we're going to look for the pressure reduced line. That's about 0.86. It looks like from this to me, that line's going to be the closest to this 0.85 line. So maybe a little bit above it. So I'm going to find like about 2.5, maybe a little bit lower, go up to this 0.86 line, maybe about right here, come over to my x-axis, and it looks like this Z value is about 0.84, 0.85, 0.83, 0.86, whatever. I would say this is about 0.84, but any of those is fine. All right, so now we have our Z value from these. So Z is equal to 0.84. Oops. What in the world? So therefore, we can take our ideal specific volume, multiply it by this correction factor, and get our actual specific volume. So Z times specific factor, specific volume ideal, 0.84 times 0.026 cubic meter per kilogram. This is equal to 0.022 cubic meter per kilogram. So if you were to do the error, which you weren't asked to do in this problem, but if you were to do the error, remember, is something similar to observed minus actual over actual. So you would compare B minus A over A or C minus A over A, because A is going to be our actual. This is what we looked up. So as you can see, our C value is much closer to our actual value than our B value. So, so you get the value from the numbers on the green lines. No, you have to already know what green line you're using, and you get the value by lining up those green lines that you need. Yeah. Yeah, so you don't have the x-axis and y-axis meet in these questions. You have the x-axis meet the line, the temperature reduced line. And then you follow that over to the y-axis. All right. Other questions? All right, so I want to give you one thing to work on just to make sure that you understand.
I'm sorry, I got a question real quick.
Yeah.
I'm just trying to make sure I have this clear. So you're basically saying that we don't even really need to, or that the TR are the green lines essentially?
Well, there's two sets of green lines. There's VR and TR. So temperature reduced, and we have volume reduced. So volume reduced goes this way, temperature reduced goes this way.
So it just depends on which one you have is what you're meeting with.
Right. So if in a problem you have temperature and pressure, you're going to be using temperature and pressure. If you have temperature and pseudo-reduced volume, you're going to be using, or I'm sorry, if you have pressure and pseudo-reduced volume, you're going to use pressure and pseudo-reduced volume.
So ours, since we're doing the 0.246 for our x-axis, when you go up, that's meeting right about where that 0.85 is on the table.
Yeah. So it meets here, right? Because you know your temperature reduced, you know your pressure reduced. You're going to find where those meet up and then use that to get Z.
Okay, so then it's just an estimate from there.
Yeah. But if you had Z and T, you could also find P. Or if you had Z and P, you could also find T, right? So you're just kind of looking at how these are all interconnected to each other, following lines, following whatever.
All right, cool. Thank you.
Okay. So I know there's only a couple minutes left. I tend to always end early. So there's example 312 in your book says determine the pressure of water vapor. Determine the pressure of water vapor at 600 degrees Fahrenheit and 0.5143 cubic feet per pound mass using A, the steam tables, B, ideal gas, and C, generalized compressibility chart. I'm gonna just write GCC. So this is the example in your book. Work on it yourself, check yourself with the example. For those of you with the international edition, this is not going to be Fahrenheit and this will not be cubic feet. Find this example problem and work it with your own Celsius and probably Pascal. For this one, you're going to be using your pseudo-reduced volume, and you're also going to be using the equations in a slightly different way. So see if you can work it this way, really hammer home the concepts that we went over today. We will be having an in-class problem review on Friday. So if you have any questions about this example problem, feel free to ask me on Friday. So we're going to be doing example problems on Friday and on Zoom or in person. No, so far the exam averages are pretty high, so I'm not thinking I'm doing any extra credit. But you don't have to do it, but do it if you would like more practice or if you are confused about things. I haven't finished all the exams yet before anybody asked, but so far the averages are pretty high. It looks like there's going to be several people who get 100. All right, so with that, have a good rest of your day, and I will see you all on Friday.
Have a great day.
Have a good one. Thanks.